Hey guys, what is going on? Welcome back to another video. This is going to be the first video of a series that we're going to do where we're going to go through the power system in great detail for specific applications. For our first application, we're going to be looking at radio control boat power systems. We're going to cover every step of the way that you need to take in order to determine the best power system for your specific application, being our radio control boat. What we're going to do is we're going to go through the steps listed on the board, and then we're going to dive deep into each of the steps so that we fully understand what is required and that we can pick our power system based off of that. Our first step that we have there is we need to know the hull type that we're dealing with. Our second step is to measure the hull length. This is, of course, needing to be in inches. Our next step there is to calculate the wattage. This is going to be the first step that we break into detail very shortly here. Our next step is we need to determine the voltage and the current that our setup is going to run at. This is very important, and the color coding is there for a reason. The first few steps are going to be matched up together, and then the next couple in black there are going to be almost like the similar steps. So step 4 and step 5 are going to be much more or less the same thing there. And where number 5 is we have to select our battery pack. Once we know what the battery pack is, then we can move on to number 6. You can only calculate what parameter you're going to use for the motor once you have that battery selection, which is then to calculate the kV value for our motor. And then once we have that, we can go ahead and select the brushless motor based off of a couple more parameters, and then we'll have our brushless motor as well as our battery already picked out. Next item here is we need to select the ESC. So this is our electronic speed control. At this point, we're going to have everything that we need in order to determine the best speed control that's going to be best fit for our system here. The next step that we can move on to is one of the most difficult steps in all of radio control, is to figure out what kind of load you're going to place on that power system. Getting this step wrong can certainly destroy the power system. We have a very conservative method that's going to help us out in how we can go ahead and select that propeller. The next item, and this is the last item, is also a very critical step for us. This is where we're going to test our setup, where we're going to have to monitor the heat that is being produced by all components of our power system. What is very critical about this step is that we're doing it in such a way that allows for the best success. And we'll talk a little bit more about the details there once we get to that final step. Now for step number 1, let's dive more into detail as to what these first couple steps mean, and then we're going to look at more detail in terms of the bread and butter of this topic, which is getting into topics 3 to 9. So let's start off, select the hull type. This is an important area because we need to know what kind of boat we're dealing with. Generally, if you're trying to pick a power system, you already have this picked out. You already know what boat this is going to go into. If not, this is where you got to start with. So select the hull type. Well, it could be anything from the examples listed there, where it's a monohull, it's a hydroplane, or it's an outrigger. You also have other options like a catamaran as well as a tunnel hull. These are important because each one of them has a different performance aspect. We'll look at that more specifically when we're going and calculating the kV for our brushless motor. The next step is to measure the hull length in terms of inches. We do need inches for this, so make sure you have that measurement already calculated or worked out for inches. If you don't have it in inches and you are working with metric millimeters, then what you want to do is take your millimeters, let's say it's 1,000, and you want to divide that by 25.4, and you're going to get inches from that. 1,000 millimeters over 25.4 millimeters per inch will give you the amount of inches that you are going to have there. So that's the first 2 steps. Now what we're going to do is we're going to dive deeper into calculating the wattage. All right, here we are. We're going to go ahead and select our own hull type, and then we're also going to select a hull length, and we're going to run with this example through every step along this process. Let's get started by selecting our hull length, which is going to be a catamaran, and we're going to have that catamaran at 34 inches long. So our catamaran at 34 inches long, this is going to be from the hull only. It doesn't include any of the running hardware that you'd find hanging off the transom of this boat. It's going to be from the point right down to the last part of that hull. That's going to be our 34 inches. From here, we're going to have to go ahead and calculate the power required to get this thing to move at a good speed. So what happens here under the calculate the power, we do have a fancy formula here. I think at one point I may end up taking this and putting it onto an application or something on the radiocontrolinfo.com website. We'll see what we can do about that. For the meantime, we can go ahead and use this formula. Now this formula was designed so that we can get a really good speed out of our radio controlled boat. Now there's a couple ways that you can approach it when you go ahead and get the final result. So let's get there first. Our power equation is going to be what we have here defined as our formula. It's going to be 4.279 multiplied by the hull length squared. HL is representing our hull length, and then we're going to subtract 163.1 times our hull length, followed by adding 1901.5. From there, what we're going to do is we're going to go ahead and place the hull length of our example, which is the 34, into that formula. We can simply use our cell phone in order to calculate what is going on here. Just make sure you follow the typical math rules in order for this to compute the correct number. Our power equation is going to give us, in this example, 1302.624 watts. We don't care about all this last little bit, so we're not worried about how precise we are, because whether it's 1302 or 1300, it doesn't matter. We go ahead and just round to a nice even number. If it was 1308, you can round to 1310 and so forth. Just pick a number that looks nice and rounded off. So in this case, we get 1300 watts. What this means for us is our boat is going to have a very good amount of power if we go and size it according to 1300 watts. Here's where you can make a decision as to, do you want to step this up by a little bit or reduce it down a little bit? This is completely up to you. I would not expect someone who is new to radio control boats to go ahead and bump this value up. If anything, bump it down, by 5, 10, 15%, whatever you're comfortable with, and that'll get you a decent speed. In terms of what speed it's going to get you, that is very dependent on your entire setup as a whole, and we're not going to get into the speeds that this is going to achieve for you. If you want to know more about speed, you can hop on the radiocontrolinfo.com website and type in all the parameters once we're finalized with our setup into that, just to get an idea as to where you will be. Hey guys, the next step is to go ahead and lay out all the different battery options. In this case, we want to determine the voltage and the current that we're going to run on. However, the voltage is primarily determined by the battery that you select. So what we've done is we've listed it out in terms of our 2S. We've gone by 2s all the way to 10S, just so you can see what you can do with the power system. At 2S, we're going to use all the nominal voltages so that we have an understanding as to what voltage we're going to be dealing with if we go ahead and select one of those cell counts. If we look at the 2S at 7.4 volts nominal, we end up getting 175 amps from that setup. Now keep in mind, the way that we're going to go and determine these values in red, this is the current, this is the amperage. We know that voltage multiplied by current is going to give you the output in watts. And we also know that we're going ahead with 1300 watts of power. In that case, we can take our 1300 watts, sub that into our formula, equals our voltage, which is going to be 7.4, and we need to solve for current. The way we solve for current is we take our wattage and we divide it by our voltage, and that gives us the 175 for our 2S. We repeat that for all the different options all the way to 10S, and you can see as we go up in voltage, we're coming down in current. Now, one of the biggest things that we have to do next is make that selection as to what we're going to go with. We can technically go with any of these setups. However, there is one that I would prefer to have based off of a number of different factors. One, you can check out the radiocontrolinfo.com website. It will make suggestions as to what cell count you should go with based on a length of hull that you have selected. In this case, it will probably suggest that 4 to 6S is within that range. You can even go further than that on both ends. However, it is not necessarily something that is suggested. The next thing is, I know that 6S LiPo speed controls and components and lower are going to be a little bit more cost friendly. So that's another reason why I'm making the selection that I'm going to be making, in which case we've boxed off the setup that I would choose for this specific hull type. That is going to be a 6S setup at 22.2 volts nominal for 6S, drawing approximately 60 amps. Now this is the target. We're going to try and draw 60 amps from it in order to produce our 1300 watts. However, However, when we go a little bit further into the motor, you'll see what we end up doing there, because we want to make sure that we future-proof our setup, just in case we want to bump up the power, and we want to make sure that our system is going to be reliable. This is what we plan to pull from our system. Once we know the power that we're going to go with, 1300 watts, the next thing is we're going to go ahead and select that lithium polymer battery pack entirely. What we know so far is that we went through and we picked a 6S pack at 60 amps. We plan to run that 60 amps. Now we're going to go ahead, figure out the capacity that we need, and we also have to figure out the C rating and then exactly how we plan to wire it in our hull. Let's go through all those steps, starting with our capacity. 5,000 milliamp hour is the common typical battery size that is used in these boats, and that is what is recommended for essentially all radio control boats, a minimum of 5,000 milliamp hour. If you have extra room in your hull, go larger. More capacity is always better. The weight is not necessarily a problem within radio control boats, as long as your hull is strong enough to carry it and throughout all the different forces that that hull will end up going through. The next item is we want to determine the maximum discharge current that we're going to need for that battery in order to calculate the C rating for it. In order to calculate the maximum discharge current, we take our original current that we ended up identifying, this is that 60 amps, we're going to multiply it by two different factors. The 1.3 factor is that factor for us in case we want to go up a little higher in power output for our setup. The second factor is the LiPo factor of safety. Now, typically I recommend anywhere from 1.5 upwards of even 2.0. For this video, we are going to go with a nice conservative 1.8. Yes, you can probably get away with going with a smaller number here. If you want to go and multiply it by 1.5, that's fine. All you're going to do is reduce the reliability and the lifespan that you can get out of that battery pack. If you go ahead, use all these numbers, we get a maximum discharge current of 140 amps. And because of that 140 amps, we now can go ahead and determine what our C rating is going to be for that specific battery pack that we choose. The C rating is going to be, you take your maximum discharge current and you divide that by the capacity of your battery pack in amp hours. Here we have it in milliamp hours. You just knock off those 3 zeros, divide it by 1,000, and we get 5. We go ahead, plug the 140 into our formula, we divide that by 5, and we get a total of 28C. There's probably not a battery pack that you're going to find at 28C. However, what you can do is round to a nice even number. Here we round up to 30C. You can probably get away with going with a 25C pack at a reduced amount of reliability and lifespan of the battery pack. However, giving you that extra little bit is going to help. In fact, if you can afford it and the size of the battery doesn't affect your overall setup within your hull, you can pick any value, any C rating larger than this value here. Typically, I always like to get at least 45C or higher throughout my entire lineup of batteries. That's my minimum target that I try and achieve, even if this is what the formula tells me. What you're going to gain is just better performance and better reliability for everything. Now we have one last thing to figure out, and that's how we're going to go and wire our battery. Now, typical catamaran hulls has two areas where you can have the battery pack. You want to put one pack in one of the sponsons of the hull, and you want to put another pack in the other sponson of the hull. Because that, some cases, you don't want to buy just one 6S pack at 5,000. You may want to actually split it up so you can balance it correctly. In order to do that, you have two options. You could either use series wiring or parallel wiring. Depending on what you're going to do, and this might be because you already have battery packs at your house that you can use in this setup, you may want to go with one over the other. In this case, you do have the two options. What most guys are going to be doing is they're going to end up running that series configuration. Now, what you can do is you can go ahead and buy two 3S battery packs. You want to make sure that you have that 5,000 milliamp hour or higher, and you want to make sure both those battery packs have the same C rating as we've calculated or higher. As long as all those values are the same, then you can go ahead and run two 3S packs and place them in series. Or your other option is, if you want to have another different way of looking at it, to split it up into two separate battery packs, you can use parallel wiring by getting two 6S battery packs, but instead of the cell or the voltage being halved, you're going to halve the amount of capacity there. Again, C rating has to stay the same. We're not touching the C rating. That is a constant. We're going to go ahead and run two 2500 milliamp hour packs in parallel. So combined, those will end up achieving our 5000. In both of these scenarios, whether you pick this single battery pack or you pick this multiple of battery packs, you're going to end up with the same exact result, no matter which way you slice up the battery packs here. And that really covers it for our battery selection. Now we know the haul, we know the power that we're going to run, and we know the battery pack that we need for our setup. The next item that we have to go through is we want to determine the kV value for our brushless motor. And after we determine the kV value, we're going to want to go ahead and pick the size of the motor that will be able to handle the power that we plan to run. So let's go ahead, determine that kV value. What we're looking for is a maximum unloaded RPM between those two values, around 22,500 to about 33,000 RPM unloaded. Now that is based off of a range that's going to be relatively safe for the average sport boater, or if you're new to boating. If you are new to boating, you want to be on the lower side versus the higher side. Higher side is going to yield more performance for you. Now the way that we go ahead and select within this range is by using this arrow here. We have below it a bunch of hull types to choose from. That goes from, on the left hand side, a monohull, catamaran, tunnel hull, and then ending up with our hydro and rigger. And that's, of course, our outrigger. On the right-hand side, you have the high-performance hulls that can definitely benefit from that higher RPM. We have, however, selected the catamaran for this. This is where that comes in handy for us. We want to pick somewhere in the range that is listed there. What we're going to do is we're going to pick right on that high side just to get that added performance benefit. And that's going to be around 26,000 RPM roughly that we have selected. Now you can go ahead and pick anything for that specific hull along this line. However, if you pick more towards this side of the line, it is going to be more difficult to get the power system down correct. And that is going to be based off of just reliability and making sure that it doesn't become too difficult for you to get the perfect prop to match it up correctly. You're not going to have a big margin of error where if you get something wrong with the prop and it's not working out, and if you don't quickly swap it out for something else, you could end up blowing that system up. And that's what we want to avoid. So if you're relatively new to this, you want to stick to that lower side of the range, and especially if you have those type of hulls that can certainly benefit from a larger propeller operating on lower RPM. And as you get into the high performance, like we said, higher RPM, going to be using a smaller propeller. That's kind of the mindset that we need to have there, is more RPM is going to drive the propeller size that we end up with. And we'll get to that spot within the video very shortly. So now that we have our unloaded RPM, we sub that value right into our formula of kV is equal to the RPM divided by our nominal voltage. And of course, our nominal voltage that we use is going to be the 6S pack, which is 22.2 volts. We go ahead and compute that, and it gives us 1260. Now 1260, that's going to be our kV value for the motor that we want to select. Now that we have a kV value, we can go ahead and choose the size of the motor that we want to go with. Here we're going to have the motor wattage equal to the wattage that we initially calculated multiplied by 1.4. Now this 1.4 value is going to be the value that represents the multiplier for us to, if we later in time want to get more performance out of the motor, we're going to be able to do that because we're going to chew into this coefficient or factor a little bit further. And another area is we want to not be riding right on the limitation of that motor. We want to be somewhere up above it by a good margin. So we get that multiplier of 1.4. And we want to make sure for a little bit lower here that we're following this in-runner only note that I've suggested. So here we go with the calculation, and we get 1800 watts of power is what our motor requires. Now the way we can actually compute this into a size is by using this formula, where our motor size is going to be equal to the wattage that we just calculated divided by this 4.5. What that's going to do is it's going to tell us the size of the motor in terms of grams. Now this isn't a close approximation. In-runners tend to be more efficient than out-runners, especially when in boats when we're going to go ahead and water cool them, meaning we're dropping water right on a large amount of surface area. This is why it has an in-runner only. If you end up using an out-runner, this number of 4.5 is going to become more closer to a 3 or 3.5. Somewhere around that region is what you're going to be looking at for an out-runner. Now, one of the things that you want to do here is then go ahead and select the size of motor on one that you can find that matches this 400 gram value that we're looking for. In my case, I ended up I found the exact motor that's going to work for our setup. It happens to be a 40 by 82, and these are in dimensions of the motor, so you have the diameter and the length of the can, and it's going to be at a kV of 1250, which is very close to the 1260 that we initially calculated, so that's going to work. You want to make sure the kV is in very close approximation of that. And the motor, this is the only thing that was outside of what I was looking for. The motor size is actually 445 grams. It's a lot heavier than the 400 that we calculated. Remember, this is going to be a conservative value for us, this 400 grams. Now that we got 445 gram motor, we're looking at a total wattage that we can get out of that motor of well over 2,000 watts. So that is going to be super reliable for us. We're going to be able to, bring up the power significantly within that motor. It's definitely not going to be one of our limiting factors, and that's okay. We can definitely handle a 445 gram motor in a 34-inch long haul. That's not going to be a problem for us. Let's go ahead and add the motor up to our specification list here. All right, now we're heading into the last 3 steps for selecting the power system in our radio-controlled boat. The last 3 steps include talking about the speed control, making a selection for what we're looking for there, then selecting a prop, and then going through the testing of our entire power system. Let's start off by talking about the specifics for selecting an ESC. This is by far the most simple part of the entire process, selecting our boat power system. We already know the current that we plan to run as well as the voltage that we plan to run. In this case, we know we have to make sure that the speed control is going to be okay for 6S since this is what we picked. If you happen to pick an 8S setup or a 4S setup, then you're going to have to use a speed control that is applicable for that rated cell count. You cannot play around with that value. Whatever you select there is definitely a hard number. So then the next thing that we have to look at is the current that we plan to run. We plan to run that 60 amps. Now we got to see how we can put that in terms of our speed control. We're going to go ahead and multiply that value by 1.3. Now this first factor is going to be based on us not being happy with 60 amps in the future and then pushing that system even further. So we're going to give us 30% of room where we can actually increase the power by that amount. Now the next factor is going to be the headroom of the speed control. We don't want to be running anything in our power system right at the limit, which is why we're always oversizing by quite a bit. And we're also being conservative so that we can get the reliability out there out of that system as well. So that's why we have those 2 factors. If we go and make the calculation there, we get the current is equal to 101 amps. Now it's pretty hard to find a speed control at 101 amps, and it might even be hard to find a boat speed control at 100 amps. In this case, what we can do, since the cost is probably not going to be that much difference between 100 amps and 120 amps, we go ahead and round up to 120 amps. I know we can get speed controls rated at 120 amps, and that is definitely going to work for us. Now, one thing to keep in mind is you do want to get a speed control that is water cooled and is sealed. It is best if that speed control is got an IP rating so that you know that it is waterproof to a certain degree. Speed controls, if they get wet, bad things can happen. So you want to make sure that you're protected there as well. This makes our final selection being a 6S speed control rated for 120 amps, and that we know is going to be conservative for what we plan to do with it. Now the next part is going to be moving into our most difficult part of our power system selection, which is going to be the load that we apply to that power system. What happens here if we don't put a significant prop on it? If we put no prop at all, the power system is going to pull no power. It's not going to develop much current, and it's certainly not going to be doing much work for us. If we put too large of a propeller onto our system, we're going to pull too many amps, and that can lead to major problems with our power system. That's why this is important, tied in with the final step that we're going to be talking about shortly here. Now we have it here as select a prop to start, and there's a very big reason why I boxed the word to start. The words to start is boxed off because this is intended not to be the final propeller that we use with the boat. This is the propeller that we want to use to get an idea as to how our power system is going to react and the types of temperatures that we're going to see and so forth. Once we have that propeller to start and we can see what it's doing in terms of performance, then we can go and change the propeller from there. And that's what we expect to do. Oftentimes I bring with me at least 3 or 4 propellers to try. And even from there, I'll try many more just to see what happens and how the boat responds. And we'll talk a little bit about that when we're talking about testing the setup. The way we go ahead about this propeller selection is we use another fancy formula. It's not too hard. We can find a calculator right on our phones. We can have the exponent function, and that's all we're going to need for this specific one. We only have a few values to put in there. We can get the propeller diameter out of it. That diameter is going to be in terms of millimeters. So here we're flip-flopping between the imperial and metric system, I understand. Our formula is going to be the prop diameter is equal to 11.452 multiplied by the wattage that we initially started with, raised to the exponent of 0.1787. We go ahead, plug in our wattage, which is going to be the P diameter is equal to 11.452 multiplied by the 1300 raised to that exponent. When we go and compute this out, we get a prop diameter equal to 41.24 millimeters. Now that is going to be the diameter that we calculate. Keep in mind that is definitely going to be conservative for our setup. That is what it is intended to do, is to give us that reliability so that we can go and throw this on our boat knowing that we're not going to blow anything up. Now one thing to also keep in mind is this does not tell us the pitch in order to have for our propeller. What we're going to do is we're going to keep this fixed no matter what hull you're going to end up running. Try to keep our pitch ratio of 1.4. If you're looking at Octura type props, that is going to be an X4 in front of the number that you're going to pick. An X440, for example, would be the prop that has a 1.4 pitch ratio and a 40 millimeter diameter. If you wanted to know what the pitch is, you just multiply the pitch ratio by the diameter and you get the full pitch. Now, one thing to keep in mind here is if you are going towards the lower side of RPM or higher side of the RPM, this is going to show you which way you should round. They don't make a 41.24 millimeter in that specific brand. You may find another brand that does, however, this one doesn't. If you have to round, you want to round down if you have the high RPM on that range that we showed you in a few whiteboards ago, or if you're going with a lower RPM range, you're going to want to go on the higher side. Now this is important because a lot of the times you could have, let's say, a monohull or even a catamaran that may struggle to get on plane because the propeller that this is going to calculate is too small. In that case, you will be forced to use a larger propeller, and that's more so for the monohull that's going to be running lower RPM values for our unloaded RPM. So that is definitely something to keep in mind. Now the prop selection is not done just there. We're only getting started. The next thing that we're going to want to do is we want to test that setup. Now to test that setup, obviously we have to have our hull built. Everything's got to be in it. You're going to want to go ahead and seal up the hatch. Use a good tape to seal that hatch, and then go ahead and run that boat. Now it's going to be a little bit difficult in the beginning because what you're going to want to do is you want to take your setup, you want to charge those batteries, seal that hull off with the hatch tape, and then what you want to do is throw that hull out there on the water and run it for a very short period of time. We're talking only like 30 to 45 seconds. Then you want to bring it in, test the temperatures, and if everything is good, then you want to go ahead and increase that time that you're going to have that hull running out there on the open water. And if everything comes back after that duration of time and you're still good on temperatures, then you can go ahead and increase it until you get to the point where you're discharging a maximum 80% of the original 5,000 milliamp hour that we were talking about. Now the temperatures that you're looking for is the ones that we talk about in all the videos, where a maximum on every component, that is your batteries, your speed control, as well as your motor, of 60 degrees Celsius or 140 degrees Fahrenheit. Certainly you do not want your battery to exceed that. That is the most critical component for this temperature. Once you know that you're not exceeding those temperatures, then you can go ahead and increase the size of the propeller. If you are experiencing too much heat, this is an indication and suggestion that you should reduce the amount of propeller that you're using in terms of the diameter. One thing that will help you out during your run is if you can data log that run. Data log is a good way to understand exactly what your power system is doing. It's impossible to take that boat and place it on your workbench to understand how much power it's going to draw. The only way you can figure out how much power it's going to draw is by sending it out on the water and letting it go wide open throttle so that you can get all the data. And what you're going to look for on that data set is the maximum current that you're pulling, so the maximum amps. You want to compare that against where you expect it to be. And another item worth mentioning is the ripple voltage. You want to make sure that the ripple voltage is less than 10% of the voltage of your battery pack, nominal voltage of your battery pack. If you're able to do this through a data log and verify that everything is okay, that's going to maximize the reliability of your system. Now, I hope this video helps. This is certainly the most complex video that I've done to date, with the most amount of information in order to be passed on, especially looking at ways that I can figure out exactly how we can go ahead and make that propeller selection and the wattage selection for our radio control boat. I don't think there's a video out there that is similar to this for radio control boats. I hope to do one for radio control cars as well as radio control airplanes sometime in the near future. If you like that video, please go ahead and smash that like button. And if you want to see more content similar to what we've gone through in this video, don't forget to hit the subscribe button so that I can see you in that next video. Thanks a lot for watching, and I'll see you next Monday.